recording. And so here's what I know about the exam. I sent you guys a note back during spring break. Our exam date now for the stats exam is May 22nd. It was pushed back essentially a week from our original date. It will consist of 2 questions. Both of them will be open response. One of the questions is worth 55%. One is worth 45%. I would expect that they'll be basically what you're going to be given is roughly, I don't know, 20, 25 minutes to write your solution, and then 5 minutes time to submit it online. And how that works, I'm not sure yet, but you will be able to submit online while you're taking the test. Then you'll go to the second question, and same thing, 20 to 25 minutes worth of work time, 5 minutes to upload your response. How that works, again, I'm not sure yet. I will be part of a video conference tomorrow night with the College Board. They're going to be giving us this one's specially designed for math teachers. So we'll be talking specifically about how the tests will go, what types of questions there'll be, things like that. And so on Wednesday, I'll share with you what I know. But bottom line is, I get an update from them about once a week, and what I get is I end up sharing with you guys via Classroom or email or something like that. Now, my question is, I know many of you have other AP classes. Do you know what the dates for those tests are? Is there any of you, let me ask it this way, are there any of you wanting to know what the date of your tests are for other classes? If you are, I have access to an overall schedule that lists all the classes, not just the math ones. I can look it up for you. I won't take time to do it now, but I will look it up and I'll reply to you individually. So is there anybody that wants to know another AP exam date or time? If so, just yell out.
Me.
Okay. Skylar, what do you need?
AP Chemistry, AP Environmental Science, and AP Lit.
AP Chem, AP Environmental, and AP Lit.
Holy crap.
That's a few AP classes, Skylar.
Yeah.
Nothing like keeping yourself busy.
Yeah.
Okay. When we're done here, I will look that up and I'll send those. Actually, I'll just post the schedule. Crap. It's a 1-page PDF. I'll just post it on Classroom and y'all can all look at it. It looks like all of the tests are being postponed a bit compared to their original date, and they're all being streamlined considerably. The good news is, what I've been told and what I've read so far, a 3, a 4, or a 5 on this test still means the same thing it did on last year's test. In other words, colleges have affirmed that they will give you the same level of credit for a 3 on this year's exam that they would have given students for a 3 on last year's, or a 4 or a 5. Same thing. So that's good. I'm interested to see what kind of questions they're going to be asking, because one of the guidance that they gave me is that the questions should all be answered with a simple 4-function calculator. That means plus, minus, multiply, and divide. So I don't anticipate there being a lot of complicated calculations in these exams unless they just give you the formula or give you an intermediate result. I don't know how that's going to work. I'll know more on Wednesday, and we'll talk about it. We'll talk about it more then. But for right now, guys, we'll just keep doing what we know to do. I'll get you as prepared as I can, and we'll be as ready as we can be. I'm prepared to go all the way to May 22nd online if need be to get you guys ready. You know, hopefully we'll get back in the classroom before that. But if we don't, I'll do everything I can to help you guys be successful. So that's my promise. And we'll work from there. So let's, unless there are any questions, we'll switch gears to kind of talking about, pick up where we left off last 2 weeks ago. Gosh, it seems like a lifetime ago, but 2 weeks ago. Any questions about the exam at this point? Okay, so what were we talking about 2 weeks ago? Well, we were talking about 2 ways to draw conclusions about a population from taking samples from the population. The first one we talked about was calculating a sample proportion. In other words, we were asking questions of the population that could be answered with maybe a yes or no answer, or anyway, we were calculating a proportion. The typical example that we were talking about before we got out was the red chips and blue chip in a bucket. What's the proportion of red chips? So that's a sample proportion. The second question that we started asking of a population was a measurement question. What is the height of the population? What is the age of the population? All of those things that are measurements. And so it makes sense to calculate a sample mean from the samples that we take. And so we talked about calculating a sample mean. We talked about how do we describe the shape of the sampling distribution. There are ways that we can know whether the sampling distribution of sample proportions is normally distributed. There are ways that we can find out whether the sampling distribution of sample means is normally distributed. And those 2 things are separate. One of the biggest difficulties my students have had in the past with this topic is recognizing that the sampling distribution of sample proportions, or the shape of the sampling distribution of sampling proportions, is determined differently than the shape of the sampling distribution of sample means. And so you got to keep those things separate. Over the next day or so, we'll talk about that a bit more, and hopefully it'll come back to you, as I'm sure many of you have gotten a little rusty here. Quite honestly, I've gotten a little rusty. But anyway, that's where we are. We talked about sampling distributions of sample proportions, and a sampling distribution of sample means. Now, for both of those, the sampling distribution is the population of all possible samples of a certain size, of size n equals 20, 25, 50, 100, whatever it is, all possible samples. We can never get that. Those are huge numbers if you have a big population. And so what we do is we take a reasonable number of different samples of the same size, we plot that data, and we draw conclusions about the shape, the center, and the spread based on what we've talked about. So the sampling distribution is always the total number of samples that can be drawn from a population of a particular size. So that's always a really, really, really big number. We never can get there from here. So we will settle with taking a goodly number. What is a goodly number? I don't know, 20, 25, 30 different samples. And then we'll plot our data from there and go from there. So what I want you to do, we'll just walk through a couple of review questions that I think should be pretty straightforward. So if you've got your textbook, go ahead and grab your textbook and turn to page 458. This is the title, chapter review exercises. So these are review questions. And today what we're going to do is we're going to take a couple of questions dealing with the sampling distribution of sample proportions. I think these are all proportions. Let me I think so. Well, we'll dig into it and we'll see. So page 458, let's look at the first question. The title is Bad Eggs. The sale of eggs that are contaminated with salmonella can cause food poisoning in consumers. Someday when we have time, let me tell you what it's like to have food poisoning from a bad egg while you're stranded in China. I almost died, just to make a long story short. But anyway, a large egg producer takes a simple random sample of 200 eggs from all the eggs shipped in one day. The lab reports that 9 of these eggs had salmonella contamination. Unknown to the producer, 0.1% or 0.1% of all eggs shipped had salmonella. So what we're asked to do here is just identify the population, the parameter, the sample, and the statistics. So this is kind of a bell ringer question, just making sure we remember the terminology. Okay, so let's talk about the population. What is the population here? Somebody want to chime in?
Is it all of the eggs that the people produce? So.
Yeah, it's all the eggs that were shipped in one day. We don't know how many that is. It doesn't say. We just know that it's all the eggs that we shipped in one day. That's the population. And what's the parameter that describes that population? Remember, P for population and P for parameter, those two things go together. What's the parameter that describes the population?
0.1%.
0.1% actually were contaminated with salmonella. Okay, so that describes the population. And notice, finally, we get a little bit of realism salted into the question. Unknown to the producer, 0.1% of all eggs shipped had salmonella. That's the truth of the matter. The producer, the manufacturer, almost never knows what's true about the population. We almost never know that value. Okay, so this is a rather textbook type question, really designed to help us review the terminology for parameter, population, statistic, and sample. But bottom line is, in reality, you almost never know that value. And so that's why we do sampling, is to estimate that value, to come up with an estimate. Okay, so what's the sample now?
The 200 eggs.
200 randomly selected eggs from one day shipment. So the sample size is N equals 200. And we have no idea how many eggs were shipped. We don't need to know that, but we do know that we took a pretty large sample, 200 eggs out of a day shipment. that's probably a pretty big sample. So what's the statistic?
9 had salmonella.
Nine out of 200. Now remember the statistic. We're gonna express that in terms of a proportion, and so we would say that p hat is 9 over 200. That's our statistic. P hat, remember the population P, the population parameter was 0.01% or 0.001, or if we wanted to write it similar in a fraction, we would say that's 1 over 1,000. Okay. But in any event, we're comparing the difference between p hat, the sample value, the sample proportion, and the population parameter of 0.01. Okay, questions there? We should find that one pretty straightforward. Hopefully that begins to sink in as something. Oh yeah, we talked about that. I remember talking about that. Any questions there? Good news is we had no calculations to do there. We could, for comparison's sake, we could calculate this and say that is 0.045, right? 9 out of 200, 4.5 out of 100. Yeah. So how does the sample proportion compare to the population proportion? Well, it's pretty high, right? 0.045 compared to 0.001. Honestly, if I'm the egg producer and I get a sample proportion this high, I'm going to be very, very nervous. 4.5% of the eggs that get shipped out of there contaminated with salmonella, that's a big deal. So if I'm the egg producer, I'm gonna do what I can to get those eggs back, and then also begin inspecting all the eggs I've got ready to ship for the next day. Okay, that's question 1. Okay, so let's dig into questions 2 and 3. They all refer to this dot plot that you see below. I'll read the scenario. Researchers in Norway analyzed data on birth weights of 400,000 newborns over a 6-year period. The distribution of birth weights is approximately normal, with a mean of 3,668 grams, standard deviation of 511. In this population, the range, the max minus the min, is 3,417 grams. We used Fathom software to take 500 simple random samples of size n equals 5. Notice the sample size is 5, and calculate the range for each sample. And the dot plot below shows the results. Okay. So we took data over a 6-year period from 400,000 newborns in Norway. There's a lot of data collected. 400,000 data points is a big number. And so we want to now begin to look at what we might see from these samples of n equals 5. Okay. So 7.2 part A says, sketch a possible graph of the distribution of sample data for a simple random sample of size 5 with a range of 1,000 grams. Okay. So a possible graph of the distribution of sample data. First of all, let me ask the question here. Are we dealing with a sampling distribution of sample proportion or a sampling distribution of sample means here? There's a really big clue in the context of the question there. Yeah, yeah. The question talks about a
Mean.
the population is normally distributed with a mean of 3,688 and a standard deviation of 511. So immediately when you read that there is a sample mean and a sample standard deviation, in your mind, you should be realizing, you should tell yourself, okay, I'm talking about a sampling distribution of sample means at this point. And so everything I'm going to be doing is based on measurements. I'm not going to be counting how many red chips are in the bucket. I'm going to be measuring things. And in this case, what we're measuring is the weight of newborns. Okay, and so the rules for calculating calculating the center and the spread for that sampling distribution and the way to determine the shape of that distribution is different because we're talking about sample means. Okay, so a possible graph of the distribution of sample data. Well, so imagine imagine you have 1,000 different 1,000 different data points and you select 5 of them. What's that going to look like? Well, honestly, probably the best way to describe it is to describe it as a dot plot, similar to what we've got, but we're only going to have 5 dots on this dot plot because the sample size is 5. Now notice the description here says we want to sketch a possible graph of the distribution of sample data. In other words, we want to sketch one sample of size n equals 5 with a range of 1,000 grams. So we need to what that does is that calibrates the horizontal axis for us. And we know that we're going to expect the data to be centered around the mean of the population data. We would expect it to be centered around 3660. But we want a range of about 500, or I'm sorry, a range of about 1,000. So what I'm going to do is I'm going to put the middle of my dot plot at 3,600. Okay, and I'm going to go to the left 500 grams. So 1, 2, 3, 4, 5. And so 3,600 minus 5 is going to be about 3,100. Then I'm going to go to the right about 500 grams. 1, 2, 3, 4, 5. So 3,600 plus 500 grams will be 4,100 grams. I need to label this weight of newborns. And I'm going to give the units in grams. Now I'm going to, it says sketch a possible graph. This is put 5 dots on that graph, and it's up to you as to where you put the dots, okay? Now, I really don't think that this is, I don't know, you might get this as a possible question, but this is pretty nebulous, and it's going to be hard for a reader to grade 60,000 of these type questions when the answers can all be completely different. But it gets our mind thinking about what does a sample of 5 look like. So I'm just going to make a dot plot here of 5 dots. Honestly, so that's n equals 5. There are 5 dots there. And that is a possible graph of the distribution of sample data for a simple random sample with a range of 1,000. Now, you might ask the question, Barry, why did you pick that as the center for the data? Well, why not? Expect my sample data, since my population is really, really large, 400,000. I expect my values to be centered around that value somewhere, reasonably around there. And the standard deviation is about 500 grams. So a range of 1,000, this represents -1 standard deviation and +1 standard deviation. And so it seems reasonable. Could I have centered it at 3,500 or 3,800? Yeah, of course you could. All of those values make sense. It does not make sense to center this graph at, say, 1,000. That doesn't make sense because it would be very, very, very unlikely, based on the population, to draw a sample of size n equals 5 and get 5 data points centered around 1,000, much less just get one of them. Okay, that would be very, very unlikely, given the standard deviation of roughly 500 grams. So I picked the center point. I went at 500 to the left and to the right, and I just put 5 dots on there. That could be my sampling data for a size of n equals 5. Okay. So part B to this question says, explain why the dot plot of sample ranges above is not the actual sampling distribution of the sample range. Okay, so tell me why that's not the actual sampling distribution of sample range. Well, it goes back to the definition of the sampling distribution. The sampling distribution of sample data, whatever value, whatever statistic we're calculating. And here we're not calculating the mean, we're calculating the range for part B. The sampling distribution of the sampling range is all the possible combinations of a simple random sample of 500 from that population of 400,000. And what we've got here in the dot plot above is just 500 simple random samples. Okay, so how many other random samples of size n equals 5 can you draw from a population of 400,000? A lot. That number is really, 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 really big. Okay, and what you have here is just 500 of those dots. So the picture that's shown in your textbook is just a representation of 500 of them. There would be many, 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 many more if we wanted the sampling distribution of sample range. Okay, sampling distribution of the sample range contains all possible samples of n equals 5. This one only contains 500. Okay. Okay, so what we'll do here is we'll take a look at question 7.3, and then we'll call it for today. And question 7.3 refers back to this dot plot. Is the sample range an unbiased estimator of the population range? Give evidence from the graph to support your answer. Okay, remember, what does it mean to be an unbiased estimator? Well, remember, an unbiased estimator. Best example I can give you of the unbiased estimator is the archery target graph that we looked at the very beginning before we went out. Okay, so imagine your bullseye's in the middle. That is that represents the true value for your population parameter, whatever that is, whether that's the mean, the range, whatever it is, that represents truth. To be unbiased, I want all my samples. I want all my samples to be centered around that value. Okay, so the center of those values, if I look at all the orange dots, the center is going to be pretty close to the center of my target, of my bullseye. Okay, so that would represent an unbiased estimator. Now notice the spread, the variation is pretty high. So I've got a fair amount of variability, but at least the average distance of each of these dots from the center is going to be pretty small. Okay, so this represents a pretty good unbiased estimator. On the other hand, a biased estimator might look something like this. Okay, a biased estimator is going to look like this. All the center of the dots is pretty remotely located from the center of my population value. And so the distance between these two is some measurable number. And so this is the purple dots represents a biased estimator. The center of this group is not the center of my population mean. Now, one good thing about this sample data is that it has pretty low variability. Okay, all the dots are pretty close together, but it's not an unbiased estimator. And in statistics, that's what we're looking for. We're looking for unbiased estimators. So now let's go back to our birth weight question and ask ourselves the question, is the sample range an unbiased estimator of the population range? Give evidence from the graph to support our answer. Okay, I'm going to let you think about that for a minute, and then we'll come back and we'll talk. Anybody have any ideas?
Would it be because it's all centered around 1,000 or close to the standard deviation on each side?
Yeah, it's centered around 1,000. The sample range is centered around 1,000. Where is the population range centered around?
3,417.
3417, right? And in this dot plot, none of the samples were above 3,000. If this were an unbiased estimator, we would expect the center of the data to be around 3,400. And in this case, none of the values were even above 3,000. Okay, so this is a very biased estimator. A sample size of n equals 5 is very, very biased. It woefully underestimated the range of the population. Okay. So the answer to part A is it is not, capital N-O-T, not an unbiased estimator. Because the center of the data, as Elijah pointed out, is somewhere around 1,000. It's kind of pulled to the right a little bit, so it might be the center of that sample might be around 1,200. But regardless, it's far from 3,400 where we would expect the value to be. Okay. Part B, explain how we could decrease the variability of the sampling distribution of the sample range. Okay. This one should be an easy one. What do you do to decrease variability? In unison, we should all say the same thing.
Increase the sample size.
Take more samples. That's right. Take more samples. Remember from the very last topic we discussed was the central limit theorem. The central limit theorem is a dream theorem for us in statistics. What it says is if we take enough samples, it doesn't matter what the population looks like. The population could look like it could look like mountain ranges in the Smokies. It could be up and down, up and down, up and down. But if we take enough samples, then that sampling distribution is going to be normally distributed. So the answer we always give to reduce variability, we always want to take more samples. And anybody who would suggest taking a sample size of n equals 5 should be just laughed out of the discussion, because n equals 5 is way too small. Remember, the central limit theorem says we need about a sample size of 30 at least to make sure that we've got a good enough sample to declare our sampling distribution will be normally distributed. So more samples is always better. Now the question could be, does 30 samples, is it better than 25 samples, or is 50 better than 30, or is 100 better than 50? Well, we would have to do some calculations to decide how much better that gets us. Certainly 100 is better than 50. More is always better in this case. But is the extra work that it takes to get those 100 samples, is it worth it? Is the variability that you get from a sample size of 100 that much smaller than a sample size of 50? Well, we'd have to do some calculations to answer that question. Okay, so the key things to pull away from here is, first of all, just practicing what's the population, what's the parameter, what's the sample, what's the statistic, what's the difference between sample proportion versus sample mean. And in this case, we pull out a new parameter, the sample range. We really haven't talked about the sample range, but it's just as valid as the sample mean. But here we are certainly measuring things, so we want to think about this in terms of as if we were calculating a sample mean. And the other thing we want to remind ourselves, more samples is always better. To reduce variability, take more samples. 5 is a terrible number. 25, probably the bare minimum. 30, central limit theorem says if you got a sample size of at least 30, you're in good shape. If you had the sample size of 25, you remember, and we'll talk about it some more tomorrow probably, we can go back and do that calculation. What is the variability associated with a sample size of 25? Is it small enough for our purposes? Then we can go back and look at that. All right. Any questions? Any questions? What I want us to do while it's fresh on your mind, question 7.4, pretty similar to what we've done in 7.2 and 7.3. So that'll be our assignment from today. I'll write it up. I'll put it on Google Classroom here in a little bit, define it a little bit more for you. But 7.4 will be our assignment for the day. We'll pick up from there tomorrow. Any further questions or any last minute questions? Guys, it's good to see your faces, even if they're in little thumbnails on the side of my screen. But I look forward to this time we have together. I miss you guys. I really do. I hope y'all miss us too.
I miss you too.
All right. Well, that's what I wanted to hear. Well, y'all have a good rest of the day, and we'll get back together tomorrow at 1. Talk to you later.
Bye.